The activation function. So far we know that a neural network can contain layers inside. Each layer contains the neurons. In the Keras jargon, they are called units. Within each layer, we can modify the activation function. In this tutorial, we will try a few of them to explain which are the main differences. How can we know the many activation functions that we have in Keras? If we import from Keras the activations module .tab, we can see the activations such as the linear, ReLu, TanH, or Sigmoid, among others. If we create a plot where the y-axis represents the error and the x-axis represents the number of epochs, we can see that the Sigmoid function starts with an error of 260. As we increase the number of iterations, the number of epochs, we can see how the error is smaller, but is not optimal because the activation function of the Sigmoid doesn't work for this type of problem, which I will explain later. Nevertheless, if we use the linear activation function, we can see that at the beginning we have an error of almost 800, and as we increase the number of epochs, we hugely reduce the error until at the end we have an error of around 10. What would happen if we use the TanH or the ReLu activation? That the error is around 2500 and it doesn't improve as much as we increase the number of epochs. Now let's deconstruct the concept of the activation function. A neural network is a mathematical equation that, given the explanatory variables a1, a2, a3, an, the machine needs to optimize the best numbers for the mathematical equation in the weights WV1, WV2, WVn. How then do you calculate the prediction for this neuron, for this output? You substitute the real data. Let's say that A1 is speeding, A2 is alcohol, A3 is insurance losses, and so on. If you multiply with the weights, you will get one number, which is the value of the output, the prediction. Nevertheless, with neural networks, there is one more step that we need to do before clearing the prediction. We need to apply an activation function. In this case, the one you see represented is the Sigmoid function. What is the Sigmoid function doing? If you observe this chart, any number in the x-axis, the product of the multiplication inside the parentheses, will be limited between 0 and 1 because of this activation function, the Sigmoid. If you use TanH, it will be between -1 and 1. If you pass ReLu, the output will be 0 if we have a negative number in the product of the multiplication. If the product is greater than 0, we will get the same value because from 0 the function is linear. Now let's compute these activation functions with Python. We load the dataset, select the features X and Y. If we go to the Keras website, we can study the many activation functions that we have available. In this tutorial, I will show you ReLu, Sigmoid, TanH, and linear. The first one is the Sigmoids between 0 and 1. In the activation parameter, we could look for the documentation to check the possible values. Activation, in which they suggest linear, but they don't specify all of the possibilities. If you want to see all of the possibilities, you need to go from Keras, import activations, and then within activations, you can look for the Sigmoid. You copy and paste it in the code. Now we execute, and we can see how the epochs are iterating over the data to theoretically minimize the error. Instead of watching the huge output, we will put its the verbose to 0. And another thing you should know is that in the activation, you don't need to specify the function from activations. You could simply put Sigmoid and then you execute. We don't get any error. The function is computed in the inside. Since we are saving the result of the feed in history, we can access it, get inside the history, and there we can see the loss of the neural network as we iterate over the epochs. Now we can access the loss and create an empty dictionary to keep track of the losses of each activation function with this data. We execute and now we save the results in the dictionary with the Sigmoid key. We execute. As you should know, after computing the mathematical equation with feeds, we calculate the predictions. We observe how all of the predictions are 0 because any number from the neuron will be limited between 0 and 1. As we don't improve the error, the neural network won't know how to change its default value, which is 0. And if we evaluate the model, we can see that the model is really bad. Now we will use the linear activation, which can take any value. In the activation, we can use directly linear. We'll set the verbose to 0, save the history in the dictionary. We execute. You will see a star because the computer is processing the information. Now if we access within the dictionary and the linear, we can see at the beginning we have an error of 300,000. As we increase the number of epochs, the error is decreasing until we finally get an error of 130. Now, this time in which we are using the linear activation, we are improving the error because it is decreasing. If we check out the predictions, now they won't be 0, they will take values nearer to the reality. We evaluate the model and we get 123, which is far better than the 260 we had gotten before. Now we use the TanH, which limits the output to be between 1 and -1. We change it in the activation, TanH, set the verbose to 0, and save the history in the dictionary. We ask to the dictionary, within TanH, we can see how the error does not improve the 235 as we increase the number of epochs. Now we calculate the predictions, and they are 1 because the TanH limits the output to be between 1 and -1. Now we evaluate the model, which gives us a better error than the Sigmoid, but it is useless because all of the predictions are 1. So far, the best activation for this dataset is the linear. Finally, we will try the ReLu activation, which takes linear values with non-negative numbers. Let's see if we can get nearer predictions. In the activation, we use ReLu, verbose to 0, and save the history in the dictionary. We execute. We can calculate the predictions. They are all 0, which is an indication that in the dictionary, looking within ReLu, the error does not improve as we increase the number of epochs. And finally, we compute the score, which is 265. Finally, we use the function plot history to analyze the differences between all of the activation functions in the dictionary. We execute, and there we can see how the best activation function is the linear because it's the only one in which the error improves as we increase the number of epochs until we finally get an error of 123. whereas the other activation functions barely improve and maintain an error around 2500. In summary, let me explain to you how to use these activation functions. The industry standards, anytime that you use neural network. The hidden layers, which are the layers in the middle of the input and the final one, will have the ReLu activation function. In the output layer, we can use linear, sigmoid, or softmax depending on the target variable that we are predicting. If we want to classify the data, because the target variable contains categorical variables, if the variable contains two possible values, binary, we will use the sigmoid activation in the last layer. If it contains more than two categories, which is understood as multiclass, we will use the softmax activation function. And as in this tutorial, if we have a continuous variable, that is a regression problem in which we use the linear activation in the output layer. Now that you understand the activation function within the neural network context, in the following tutorial, I will show you how to understand the optimizer, which is the first parameter of the compile function.